Hello and welcome to the session. In today's session, we will be discussing about reduced instruction set computer architecture. Now, this architecture is also called RISC architecture and is popular in computer science for many different applications and development of processors. Well, when we talk about an architecture in context of computer, we basically mean the instruction sets only, right? And instruction sets are the one which basically determine what kind of hardware is to be integrated within a computer system. Now, instruction design primarily focuses on two basic techniques, right? And the first one which is there is the microprogrammed control unit and complex instruction set computer, which is also called CISC. Now, the basic idea in this particular architecture was that we were making very complex instruction sets. That means even for addition, we were having at least 10 to 15 addition instructions, right? So, those addition instructions were implemented with the help of microprogram control. And that is why the term microprogram control unit and CISC. Why? Because microprogram control unit facilitated the development of complex instruction set computers, and that is what we will be discussing slightly more details. Then cache and instruction pipeline. Now, these were the two things which were brought in later into the computer in the development of computer instruction sets. They actually changed the whole gambit, we say, for instruction design, in the sense that reduced instruction set computers started becoming popular, and they become in fact one of the key design architecture as far as instruction set is considered. Now, historically, if we see why complex instruction sets were needed, right? So there was a large gap in the speed of memory and instruction in the past. It used to exist, but cache has fulfilled that particular gap to a certain extent, right? So let us look into an example that suppose we are dealing with floating point addition, right? So if we have not implemented an instruction within the hardware, then how this particular stuff will be executed? First, fetching of mantissa and exponents, right? Then comparing exponents, both the exponents will be compared. Then possible shifting of one of the mantissa so that both the mantissas are aligned as per the same exponent. Then addition of the mantissa has to take place, right? And after the addition, normalization of result is also required. And finally, after normalization of result, overflow and in fact before the normalization, overflow and condition will be checked, and finally the results will be stored. So there will be a number of sequential instructions which will be required to execute floating point addition. Now, if that is the case, obviously it is going to fetch at least 6 to 7 such instructions from the memory, and the execution is going to take place. And accessing memory, since it is very expensive operation, then designer thought, why not put this floating point instruction, right, addition instruction, as part of instruction set of the computer, and just feed give the mantissa as well as exponents to those instructions, and the additions will be performed. So there will not be 6 fetch cycles which will be needed for such kind of instructions. So that way they wanted to minimize the transfer of instruction to the CPU. And then obviously when this particular instruction will be executed by the CPU, the microprogram will still require to compare exponents, possible shifting of mantissa, then performing the addition, then the normalizing and checking overflow, and then storing the result in any case is required. So these steps then in any case will be required, and they will be put in the microprogram. So once the microprogram is going to take control of thereafter, and since microprogram lies within the CPU, so there will not be any additional memory operation required from the point of view of instruction set is considered. So the idea basically was, if we can put more and more instructions within the CPU, and there was, you know, very large scale integration going on, and it was moving towards ultra large scale integration. So a lot of space was available, lot of chips could be integrated onto a simple machine on a processor and onto a chip, and that used to cause, okay, why not put more and more complex instructions within the computer domain or the microcode. Okay, however, so can it be made a machine instruction? That was the idea, right? So the idea was to make it a machine instruction so that it executes more efficiently. However, with cache memory for instruction and data, right? So availability of the cache memory brought in this particular change, and the gap between the memory as well as CPU, that got reduced drastically. So whatever you could do with the help of microprogram, you can also do with the help of cache memory. In fact, you must have heard that these days computers have the on-chip cache, right, which is instruction cache, which is L1 cache, instruction cache, as well as data cache, which is available to the processor. So that kind of a cache memory, since is available, so instruction can easily be moved to that particular place, right? And the advantage, the gap advantage which designer wanted to take by moving the instruction set into microprogram control unit or microcode kind of format was no longer available with the hardware advancements. Then the comparison was between microcode, and the microcode is basically microprogramming only, right, and VLSI technology. So control unit, which was basically used microprograms. Why the microprograms were used in the earlier times? Because it was cost effective and simpler than the hardware control. You just need to add more program if you want to append the instruction set. You don't need to redesign the whole circuit, which happens in case you are doing a hardwired control unit, because you are fabricating the circuits, right? You are fabricating the logic gates. So obviously you got to, like, it is something like if you are creating a plant, right? If you want to add more units and efficiently you want to do that particular thing, probably the same plant could be redesigned completely in a much better way, but it will require design of the same plant once again, right? If installing two different units at two different places may not be that much efficient, and that is why this VLSI technology or ULSI technology was considered not very efficient as far as moving a smaller instruction set to a bigger instruction set is concerned. Okay, more flexibility, that is what I'm talking about. The proposals were to include string matching, polynomial evaluation, floating point, etc. into the instruction set. So people wanted to move the instructions which were very commonly used, even subroutines which were commonly utilized, moving them to microcode so that they execute more efficiently. However, as I explained, the availability of cache somehow reduced that particular need, somehow eliminated that kind of a need to certain extent. So, however, a simple set of instruction may require simpler, faster logic to execute instruction faster. So, the idea is simplicity, right? Nothing much than that. If we are talking about simplicity, then what do we say as far as simplicity is concerned? Well, simplicity is when we have smaller number of large sized instructions. Do we have, that is a simplicity, or we may have smaller number of small sized instructions. In fact, it should be, the idea was in RISC, we have smaller number of small size instruction, not large size instruction in that particular sense. Okay, and in complex instruction sets, we had a larger number of large size instruction. So it was cost effective to have smaller compact programs which require complex instructions. Now, the advantage of having complex instruction set was that your program size got compacted, right, as far as number of instructions are concerned. Why? Because one floating point instruction, right, is required in complex instruction set computer, whereas in a different machine it will be converted into 6 instructions which will be executed one by one to execute a single floating point operation, right. So the program became compact, but the size of instruction became larger. Okay, but the instruction size and addressing modes requires more bit. So the more, for example, the 8086 has a large number of addition instructions, right. So now if those multiple types of addition instruction like add with carry, add with memory operand, add one memory operand with register operand, add memory operand with the immediate operand, so many different operations can be utilized. So these are all different instructions, right. So the point was here very simple. Can we reduce these instructions? Number one. Number two, can we reduce the number of instructions? Okay, so that is the idea of RISC is. Okay, are the total size of instructions smaller? The total size. Now what was done when we got smaller number of large size instructions in a program, in the complex instruction set computer. That was the idea. Why? Because we are moving instructions into microcode. So the number of instructions are more, but that means size of instruction is a bit more, but the number of instructions which are required to execute a program are lesser, right. So this is what is the concept of smaller number of large size instruction within a program. Okay. So are the total size of instructions smaller? But if I compute the total size, that is the number of instruction multiplied by the number of bits, right? So is it going to be smaller than when we are using a reduced instruction set computer? That was debated, because reduced instructions are smaller in size, okay, although the program size is larger, right? So larger program size, but lesser number of bits. Here we have smaller program but larger number of large size of instruction. So that was the dichotomy, and that was the basic trade-off which is to be considered when we are dealing with RISC versus complex instruction set computer. RISC had simpler instructions and register addressing, right. So it has smaller length instructions. So this is the key, which was the key criteria as far as reduced instruction set of computer is concerned. Then compiler on CISC also favors simpler instruction. In fact, compilers play a very important role when we are dealing with program conversion for a specific machine. And compiler designer normally favors the simpler instruction. That is what is the categorization. Even if you create very complex instruction, it may not be utilized in that particular context. It may not be utilized in the sense that the equivalent machine instruction to a programming instruction may be requiring several constraints, several characteristics, several parameters which may not match as it is. Therefore, compiler designers were not favoring the complex instruction, but rather they were favoring the simpler instruction. So then the final point here is that the higher level language instruction and complex instruction set computers. Complex instruction set computers has more powerful instruction. True, that is true. Like floating point addition is there. Even some people wanted to move case instruction into the hardware also, right? However, these complex instructions are difficult to exploit due to complexity of conditions. That's exactly what I spoke about in the previous slide. Then instruction pipelining is more difficult in complex instruction set computer. You know, in instruction pipelining work very well when you can divide a particular sequence of instruction into equal sized compartment. However, when we are dealing with complex instruction set computers, that task was difficult because some instruction, the fetch cycle may take the same time, but then decoding also may take similar time. But execution, some instruction may require only few cycles, whereas some other instructions may require very large number of cycles for execution, right? So that created a major compartmentalization problem as far as RISC pipelining, CISC pipelining is concerned. Okay. Control unit of CISC were more complex as control store is large for richer instruction set. Okay, which results in increase in execution time for simpler instruction. Now, this is a very important statement which is there. That is, control of complex instructions is more complex, right? The more complex means there will be bigger control unit. Bigger size control unit simply means bigger size microprogram. The bigger size microprogram, obviously, whenever you are having larger size, obviously some additional additional timing is required to search, to find all that kind of information. And obviously the overall effect will be that the simpler instructions which are there, like simple addition, may require more time as far as execution is concerned than the normal reduced instruction computer machine, where the simplicity leads to faster execution. Well, another characteristic which was studied during this particular time was the characteristics of high-level language programs. So these were the hardware-oriented reason. First one being the gap between the speed of main memory and the CPU started decreasing, right? In addition, then the microcode is no magical stuff. That's what was the statement. Then the support for high-level languages were not being utilized, right? So all these were the reasons in any case. But in addition to that, one of the major requirement or major problem which was there was that ultimately it is the high-level language program which are to be translated into machine language program, and they are to be executed efficiently, right? And the characteristic was very different. When it was studied, there were many researchers who studied this particular concept, Tenenbaum being one of those, and Berkeley University was another where this particular study was made. What they found that most of the variables can be categorized into three different types: integral variables, which are 15 to 25% of time, scalar variables, which are happening 15 to 60% of the time, and the arrays or the structures which were having only 20 to 30%. So array and structure which basically are very complex in nature were not utilized for more than 20 or 30% of the time. So that was a major clinching point. The second clinching point is the operations, like simple assignment. Okay, simple assignment operation was occurring for 35 to 40% of operation, requiring some kind of definitely multiplication, addition, those kinds of things, right? Then the looping constructs were just 2 to 6%, not very high. Okay, procedural calls, they were 10 to 15%. So they actually are slightly more complex. So probably they may require some support. And then if instruction, which was happening to be around 35 to 40%, you study your own programs, right? Whatever you have written. What difference you will find that you will be using more looping, because those are the programs, whatever programs which we have given to you, technically require some looping and some array. Otherwise, there will be slight mismatch from this particular statistics, but this statistics were in general for most of the programs. Now, one of the important consequence over there is the subroutine calls. Now, subroutine calls it happens to be one of the most time consuming operation. Okay, and most have less than 6 arguments and 6 local variables. Okay, and procedural cost nesting mostly less than 6 to 8 levels only. Now, this is a very important thing as far as RISC is concerned, and we are going to discuss about this particular thing at a slightly later stage, that how it affected the RISC designing and how it helped in enhancing the performance as far as RISC is concerned. But this subroutine calls are very, very important. They are occurring for 10 to 15% of the time in most of the program, and with our more and more stress onto structured programming, this particular figure is increasing all the time, right? So, but what is the important point? It does require not more than 6 to 8 parameters which are to be passed to a particular function or subroutine. You have written C program, so you write 5 to 6 variables only which are passed, then local variables maybe 6, 7, 8 like that, and then the call, like you call one program calling another function calling third, fourth, fifth, like that. So you are not going beyond 6 to 8 level of such nestings. So these were the program characteristics, and all these things, whatever we have discussed so far, led to the development of reduced instruction set architecture. So what was the logic behind RISC? Like, keep lesser and simpler instruction. Why? Because we have cache memory. So don't make very complex instruction. Even compiler support the simpler instructions. Instruction cache has greatly reduced the importance of micro instructions. So we have cache memory, right? So probably we do not require big micro instructions or big size micro programs. That means more we don't require large number of instructions within the processor. Then moving software into microcode does not make it better, but harder to change, because you have put it in the microcode, you have fabricated the chip, right? Now how you are going to change? But if it is in the software, in the operating system and in the system software, you can always you can change that particular scenario easily. Microcode can be moved to runtime libraries of the RISC also. Okay, so the runtime libraries which are easier to code, easier to change, can be utilized instead of the microcode. Then simple decoding and pipelined executions are more important than the size of the program, right? So just like I indicated the size, right? The size of the RISC program as far as number of instructions are concerned are going to be larger, but overall size may be smaller. But what is being stated over here is that simple decoding and pipelined execution. So if decoding logic is simple and we are doing pipelined execution, then it may be very, very effective than the complex instruction set where we have smaller number of instructions within a program, but the size of those instructions may differ, right? And it will be very complex to decode those instructions. Keep operands in registers. So register operand, you know, are the fastest, right? So keep operand in registers results in simpler registers results in simpler and smaller instructions. So if I use register operand, it will be, I'll be having simpler and the smaller instruction sets, okay? Because register addressing require smaller space, okay? But for that you will be requiring some more additional thing, but the logic is this, okay? Keep the operands that are to be repeatedly used in registers. Okay, so this is somewhere all those operands which are to be repeatedly used again and again, keep them in registers. And this was the job of the compiler. All right, so with this logic, okay, we designed the characteristics. Now, the first characteristics as far as RISC is concerned is one instruction per cycle. Now, this one instruction per cycle is possible because of the pipelined execution. And we would like to talk about the pipeline execution at a later point of time. But it is something like in every clock cycle, one instruction is getting output. Now that's a very tall claim to make, but this is possible because of the simplicity. So fetch operands from registers and perform the ALU operation on them and store the results in the register. This is what is the basic things which you do. Alright, so fetch operand from register, perform the operation and store values back to register. Now those things can be done in one clock cycle or maybe two clock cycles. Now we want in one clock cycle the one instruction. So how it is going to be possible? So obviously we will be going for pipelining. Then hardware control unit increases the execution efficiency. Okay, hardwired control unit, because the hardware it avoids the delay. right? So hardware control units are very, very important. It is very fast, but as the problem was that a hardware control unit is to be redesigned again and again. Now in this particular case, because of the simplicity, the design is much simpler, right? The simplicity of instructions. Okay. Then register to register operands, just as stated above. Now when you are using register to register operands, you will require load and store instruction for memory operation. So one instruction will definitely be required for loading the data and one for storing the data. Without that, this particular architecture is not going to work, right? So in addition to execution in the machine, using register operand, you definitely require load and store instruction. Then keep frequently used operands in registers. So that is where the optimizing compilers comes in, and simplify the instruction set and the control unit. Now simplified your instruction set is, your control unit is simplified, your control unit is simplified, you can implement it with the help of hardware. It is easier to design, easier to implement, easier to change, right? Then simple addressing modes like register addressing with displacement or relative addressing, just these operations, right? Just simpler addressing modes, register using register, or register with some kind of a displacement, or relative to the program counter kind of a situation. Just few addressing modes, that will be good enough. Once again, this is also going to simplify your control unit, and number of instructions will be further reduced. So that way the number of instructions are getting reduced, the control unit is getting simplified, and you are moving to the domain of reduced instruction set computers, which execute quite fast. They are not slower than the complex instruction set computers. Then simple instruction formats, right? Now the instruction format may not be many as we have in 8086, where one instruction was just 1 byte long, 2 byte long, 3 byte, 4, like that. The sizes of instructions were from 1 to 6 bytes. Here there will be only 2 types of instruction. The instructions which are referring to the memories, that is load and store, and the instructions which are executing on the register operands and storing results in the register operands. Okay. So simple instruction format. So just 2 or 3 different type of formats. So operation decoding and register operand accessing can be performed in parallel. So now that whenever we say that if we are operation decoding and register operand accessing can be performed in parallel, right? Now that is a very important situation. Why? Because now we are already talking about that if 2 steps can be performed in parallel, right? Then we are moving to some kind of pipeline domain, or a pipeline or a multiprocessor domain, or different kind of a domain, which is much more efficient than a uniprocessor domain when everything is to be done in a sequential manner. All right. Performance can be enhanced during using optimizing compilers. This is what we have already stated. In general, a microprocessor uses large areas of microprogrammed control unit. So that was the scenario. Very large area, sometimes more than 50% was utilized by the microprogram. Okay, in general, MI uses large area for microprogrammed control unit, right? So this was the case. The RISC chip devotes about 10% of this area to the control unit. In fact, even less than that. So control unit became smaller. Now that means around 30 to 40% area became vacant. So what that 30 to 40% area should be utilized in reduced instruction set computers, how it can be utilized. So that became the criteria. Okay. Then RISC architecture processor is easier to build because of the simpler logic and simpler instruction set, simplicity everywhere, right? So simplicity led to easier design and better performance. Well, it led to that, but then we had a huge area available to us in the microprocessor, right? So how we can use that particular area? Well, in reduced instruction set computers, we use large register files. All right. So now large register files in the terms of more than 100 registers were used as far as reduced instruction set computers. However, look into the first statement. It says in general about 32 registers were considered optimum. So machine designer found out the different number of registers which are required as far as processing the instructions are concerned, and they said okay, just 32 number of 32 registers are good enough for any kind of a situation. We already have 16 or 17 as far as the 8086 is concerned, so just double it, it's good enough. So why we need more registers then if 32 is required, right? So the idea was how to optimize the use of 136 register, how to optimize their use. Okay, just 32 is sufficient and 136 are available. What we are going to do with them? There's no point having those many registers, but we have the space, right? So the RISC registers file provides. So this became a RISC register file. It provides for support for call return with the help of register window. Now this is one of the most important concepts. In fact, there are two important concepts in RISC. One is this large register file and the second one is the pipelining. Now this concept goes very simply that the number of the registers, right, only 32 is required at a time for optimizing the execution of a particular program. So what we do with the others? So we have large register file, but we have no use. Well, we go back to the discussion we had. One of the discussion point which we stated was that one of the most important operation is call and return. It happens 10 to 15% of the time and the use of that kind of operation is increasing. All right. The problem here is that when you call a function, okay, not only the return address, but the content of many registers is stored and you pass lot many parameters also to the new program, right? So for example, in C you use call by value. So you are calling a function, you are calling by value. So those values are going to be transferred, right? Return address is going to be stored. The function will start executing, the control will pass, right? The function will start executing and the control will return back. Right? So there are many undue operations, specifically the passing of parameters, okay, is definitely going to be there, right? And the registers which are going to be utilized by this particular newer program, right, those old values of those registers may have to be saved because the effect of this particular function should not be carried onto the older function. So what we require is probably a different activation state, different set of registers when we call from one function to a second function. And that is what was able to we were able to do with the large register file in RISC. It was not possible in CISC, right? 32 registers are required for the normal execution of the program. But if we are moving this particular execution from one function to second function, right? So those kinds of storage of register operand and all those housekeeping operations which you are required to do for subroutine calls in RISC was greatly reduced. Now how that was reduced? Well, this is what I would like to state with you. So suppose in a RISC processor you have 0 to 9 registers which are storing the global variable. All right, and those registers, so suppose the global variables, 10 registers are good enough for storing the global variables, and remaining here you will find around 32, in fact total number of, for each function you require around 32 operand, 32 variables, roughly 32 registers. That is what is our objective. Now how those 32 registers is going to be used in RISC? So first, these 10 registers are global. So irrespective of function A, function B or function C, right? All of these functions are using these global variables. So and obviously they should not be affecting whatever changes they are making over there. It does not matter because those global variables are expected to be changed. Okay, that is why those functions will be changing it. Technically speaking, global variables need not be changed by these function A, function B, function C as side effect of functions. But anyhow, why? They may be the objective related to it. Fine. So we have this particular global variables which will be shared by function A, function B and function C, right? So remaining 22, how they will be used. Okay, so let's look into the global variable for function A. Okay, so function A, what does function A do? So obviously when the main program calls function A, right? So when you call, in fact, let the function A may be the main program itself, right? The main function itself. So main function, some of the parameters can be specified like command line arguments, right? So those command line parameters will be stored in these registers, 130, the 6 registers which are there. So once those six registers store the command line argument, okay, if there are more, obviously they will be stored in the memory and the inefficient way is going to come into picture. But in general, they are less than 6. Right? That was the program assessment. Just in 1 to 2% of the cases, they were more than 6. So therefore, we are in a very safe zone. Right? Then the local variable starts coming in over here. So there are 10 local variables. So they will, those 10 local variables, you may have more in the present scenario, but think that there were just 10 local variables. All right. So those 10 local variables then will be in 10 registers. Right? So you will be operating in this particular area. All right. And as and when this particular function A wants to call function B, all right. So function A will put those parameters for function B in the temporary registers, which are register number 161 to 121. So for calling, suppose you are calling on let's say A, B, C and D, 4 variables, right? Or let's say X, Y, Z, right? 3 variables only. So those 3 variables X, Y and Z will be put in the temporary variables, right? So they are also registers. And look into the advantage. The return value will be coming into these temporary registers and they all will also be utilized. So these 6 registers are being shared between function A and function B. Function A calls function B knows my values are here. Okay, in register number 116 to 121. So there is no physical movement except that at the time when before it calling, it moved some value over here and thereafter the call is seamless, right? Call to function B is seamless because there is no need to transfer because they are already in the required number of registers. So the value are moved to the registers of the function B. So there is an overlap, okay? So there is an overlap of registers between A and B. What for? Because function A, whatever parameter it has to pass for function B will be in those temporary variables and they are also the parameter of function B. The return value will also come back in this particular area. Then function B also moves, the context is moved to this particular function. So function B gets its own local variable in these new registers, right? So it is not affecting these older function A registers at all. It is not touching them. There are new registers which are required and the processing can take place in these registers, right? So there is no need to even touch those registers. Whereas in the case of complex instruction set computers, this area would be utilized. This area will be utilized by register B then. And then obviously they need to be stored somewhere so that we can restore the context when function B terminates. So this is not required anymore in case of reduced instruction set computer, right? Similarly, function B will call function C and similarly they will be sharing like that. Okay, so the A calling B, B calling C, all that, right? So that the nesting is going on, nesting of function is going on and one function is calling another, that function is calling another, but there is no need to store any of the values except the overlapping of register. Overlap registers are basically sending the parameters and in the return cycle they will be the return values will be stored and if B has returned then B will be passing back the results to A. So like that the overall effect of instruction, the execution of subroutines become very, very effective when we are dealing with reduced instruction set computer. The similar thing has been shown with the help of a circular buffer. All right. So A input this A in basically is equivalent to this parameter of function A, right? So A input, right? So A input came from let's say it is the calling program, that is your command line argument. All right, then A local variables. So the main program is starting to exist. This is the area, this is the context of the local variables, and then B, that is B and A, that is A output, right, in the sense. So this we are saying, okay, so this is basically the values are passed. So this is the area we are referring to. So temporary of A and B input is over here. So all these values are seamlessly passed. So B knows my parameters are here. So it will start executing, right? Then it will call C likewise by passing the values, okay, here, and C knows my parameters are here. So it doesn't, it just keeps on working in its local, with its local variable. It calls D, D calls E, right? E calls, so E calls F. But when F is being called, there is a danger that F, if F calls something else, it will be overwritten, right? So this is the saved window pointer which tells us that no, we cannot call F unless we put the A in and A location into some area in the memory as a safe values. Otherwise, F may overwrite the area of A. Therefore, we can't take that particular risk. Therefore, suppose how many windows are there? 1 window, 2, 3, 4, 5 and 6 windows are there, but in effect only 5 level of nesting is possible, because we cannot compromise on on F writing over the A. So this is the way the circular window operates. Now if F is to be called, the A in as well as a local variable, they need to be stored into the memory, right? And then only the F can be, F will be starting to execute. So it will require some time for execution in that particular sense. But that is how it works, right? And in most cases, you won't require more than 5 to 6 level. It can, and normally this window can be having 8 such sub windows, right? So if 8 windows are there, then only 7 nesting of the function nesting up to 7 will work in that situation. 8th is not going to work. So this is the way the whole thing works, right? Then the possibility of more than 7 is hardly in 5 to 6% cases. So if you require A in and A location to be saved, it will be only for 5 to 6% of the cases. 95 to 99% of the cases are going to require only 7 level of nesting. And so you can imagine the amount of saving as far as function calls are concerned, right? This would have been required if this register window is not there. This is going to be required for every call. That is the saving. Here in this particular case, in 95% case procedure call, function calls, it is not going to be required because the nesting is not going to exceed 7 or 8. So this is how RISC plays on statistics. RISC plays on the characteristics of program. And that's how those processors are able to utilize the large register file to a great extent while in an instruction call, procedure call and return. And this is one of the most important instruction, and we are emphasizing that. That is what we have been emphasizing. No, you should be writing structured programs, right? You should be using object-oriented programming, right? So all these kinds of technologies can be utilized in reduced instruction set computers very easily with the help of larger register files. And that is one of the major advantage of dealing with reduced instruction set computers. Well, that is one of the advantage. Is there any more stuff which we can think of as far as RISC is concerned? Well, there is a major advantage, another major advantage of RISC is instruction pipeline. Now, that's a very, very interesting feature. Okay, think in terms of RISC instructions. Very simple instruction, right? if there are two types of instructions when we are dealing with RISC, either the memory, memory load and store, or processor, the register oriented instruction, only these two, right? So if one instruction we require instruction fetch and instruction execute. So register to register operand, instruction fetch will be there and instruction execution is going to take place. Instruction fetch is, how instruction fetch is very, very fast? Because there is cache, right? That is why instruction fetch is going to be as fast as any microcode. Okay, and then instruction execute from the registers, right? 3 registers, 2 registers, whatever may be the case. Okay, so all register operand. Then there is a second type of instruction which will require instruction fetch, once again from cache. Then the address calculation, but the address calculation is going to be simple, right? And then the data transfer from the memory. Once again here, data transfer is going to take place with the help of data cache, right? So that is also going to be much, much faster. So all these three, like, so we have two type of instruction. One of the type of instruction will require only F and E. The second type of instruction will require F. E in this particular case is address calculation, and D happens to be data transfer. Sorry for the same code, but let's deal with that particular situation with the help of the context, right? So this is the way you can deal with as far as instruction pipeline is concerned. Now, what is the pipeline kind of concept? Now, if I have, there are 6 instructions here, 7th instruction is the return. Now, these instructions, if they are to be executed in, let's say, in a sequential manner, so how they will be executed? First FED of first instruction, then the FED of the second instruction, then FE of the next, then the FE of the next, and so on and so forth. So in effect we have 6 plus 3, 9, 9 and 8, 17. So around 17 cycles, right? Around 17 or 18 cycles will be required till we get the execution of all these instructions. But what was the principle? We just want to do this particular, so there are 17 cycles, and how many instructions? 8 instructions. That's not one instruction per cycle, right? So how RISC tried to do that particular thing? Divide the instruction into fetch, calculate effective address, and data transfer. So these two load instructions, we have these 3. Whereas in add, subtract and multiply instruction, what kind of these instruction? These are register oriented instruction. So we will have fetch and execute, fetch and execute, fetch and execute. And then finally store, once again it's a load and store kind of instruction. So it will have 3 steps. So can you see the whole thing? Now there is an overlapped execution. As soon as F of this is starting, the F of second instruction, right? So as this fetch unit, so these will be 3 separate units, fetch, execute, decode. Very simple. Fetch will be in different kind of, let's say, hardwire. Execution, second, E, that is effective address, is a second hardware, and data transfer is the third hardware stuff. So like that, you can divide your microprocessor into simpler subunits, and these subunits will be executing just part of the step, right? And maybe that you can call it a simpler microprogram in this particular case, right? And this simpler microprograms are executing in an overlapped fashion. Why? Because when the fetching has already been done for this particular stuff, this unit is no longer required. This particular instruction has moved to execution of address calculation, right? So it will be moving to this particular place. So this unit is free, so we start with the fetch. Okay, and like that. So the fetch is going on, right? And when the execution is taking place, now this is where the data conflict, right? If it is not complete, sometimes can happen, right? So this is where the possibility where one instruction per cycle may not be the case, right? But then we have to make appropriate changes on those kinds of pipeline, right? So fetch and execute. So we are assuming the data is available as soon as it has been fetched, right? So it is available, then fetch and execute, and then fetch, execute this particular cycle. So you can see in total 8 units of the time approximately. It may require 9 sometimes because of those data conflict and so on and so forth, but that is immaterial. We are almost getting one cycle, one instruction per cycle, and that is the essence of RISC pipeline. But branches in RISC pipeline are major problems, right? Branches are major problems because whether a branch is to be taken or not, okay, before that particular decision is taken, the next instruction is being fetched, right? So the next instruction has been fetched in this particular case. So this pipeline, right, may require, suppose the branch is not to be taken and return has to take place at this particular point of time only, then this pipeline is to be emptied, and emptying a pipeline will require extra cycles, right, extra circuitry, and extra circuitry make once again a simpler RISC processor much more difficult, more complex, right? Let me say branch in a pipeline means there is a branch instruction here, right? If RD is less than 0, then return. So if that particular branch, the execution will decide whether the branch is to take place or branch is not to take place. So if it is less than 0, then simply return. These 2 instructions are not to be executed. If not, then only these 2 instructions are to be executed. Alright, so that is what is the branch penalty, that the effect, whether the return has to take place over here. If return has to take place over here, these 2 instructions need not be calculated and need to be purged off. So these kinds of branch penalties are there when we are dealing with pipeline. And remember, branch instruction is occurring 50 to 60% times in programs. So it is going to be, the pipeline has to be optimized for the cases of branches. And one of the ways which was utilized in RISC was to insert a no operation, right? There is a no operation, a 9th instruction has been added, right? So effectively 9 cycles will be needed. So at this point of time, right, you don't need to empty the pipeline, right? You will come to know, okay, the branch is to be taken, or not to be taken. Okay, so you will be knowing that particular thing at that point of time. So I think the F should come here. It has just moved off this particular thing. So the FED should come here and FE should come back. So that way you will come to know that branch has to take place or not. No operation, it doesn't do anything. It is just a blank operation. Okay, so this avoids the delays your decision. The decision has been made and it delays the decision of fetching the next instruction. Remember, the RISC pipelining is small and very efficient, right? So just one no operation will be good enough. Okay, so it is not harming your interest to a great extent. So that is the way the RISC pipelining is helping you as far as delayed decisions are concerned. However, you can optimize this particular branching because the branching is taking place on the basis of subtraction, and that subtraction, okay, can happen one instruction before, right? Because it is the decision is not taking place on addition, right? So therefore, these 2 instructions can be moved before, and this particular situation is to be created by the compiler, right? So if they can be moved, not every case will be able to optimize this kind of a branching because we do not know whether this is going to happen in all the cases, but this is just a concept. As a conceptual build-up, you can optimize the delay branching by not inserting the no operation rather than just moving the subtraction and if condition before the add condition, right? So this is what? So this was the add instruction and you just moved these 2 instructions before that. So by the time you come to whether branch has to be taken place or not, right? That is going to be executed at this point of time. By that time, this instruction has already been there, so it will be fetched and executed, and there is no need to fetch this particular instruction because decision is already there, which is the next instruction to be executed. So that instruction will be fetched and the pipeline will continue, and there is no need to blank out that particular pipeline. So this is the way RISC architecture is wonderful architecture, wonderful concepts are there. I'm not saying that these days if you see RISC architecture is there, RISC-5 architecture is there, which is, previous to that is ARM, Advanced Risk Management Architecture was there. So all these architectures are there for embedded devices, and so they have open architecture, their instruction set is open. So it is available to you for your consideration, right? So these architectures are they are popular in many devices today and should be studied. Very interesting concepts, right? Not all the concepts may be utilized in a newer machine design, but these concepts gives us tremendous insights. And remember, when you are designing programs, when you are designing operating system, when you are writing system software in the long run, you will be utilizing the concepts, right? So these historical learnings are very, very important for moving ahead in your thinking, in your utilization of these concepts into a different domain where they can be utilized. So that is the essence of learning RISC processor, and not that I should be learning the RISC processor instruction set in deep set, right? In MCA you will not be required to do that particular thing, but then these concepts will be useful in the long run for your career, for your growth, for your thinking, and for your application. That is how you should be using them in your, in the future, right? Activities: study the blocks, right? Solve CYPs, solve questions given the assignment and previous year questions, and discuss with us, right? If there are any problems, you are most welcome. Thank you for being with me today. Bye for now.